Welcome everybody to the second day in this series on spectral graph theory. So, today I'd like to tell you about random spanning trees and the graph sparsification problem. Okay. I'd introduce what the setup is, so don't worry about like right now. So, what are the kind of questions that like we'd be asking today, right? So, the setup would be like something like this, that you are given like this graph G, which is connected and undirected, and we'll be interested in a bunch of questions. So even though like the graph that we are interested in, those graphs are going to be connected and undirected, in the middle of our journey, we would look at directed graphs, okay, like for a good reason, and like I'll tell you when that situation arises. So these are the kind of questions that I'm interested in. So for example, like the first question is, what are the number of spanning trees of this graph? And I'm also interested in generating a random spanning tree, uniformly random spanning tree from this collection, right? So, like this would be like not a question but a goal. So let me write it as a question. Can we generate a uniformly random spanning tree? Yes. So there is a distribution of spanning trees. Let's say that my graph has like I don't know, maybe 100 spanning trees, right? And yes, so I have a uniform distribution over these 100 trees. I would like your algorithm to return a random tree from this collection, and the probability should be that the probability that any fixed tree is returned should be exactly 1 over 100. Okay, so that's what I would like. And like of course, I would like to do this efficiently. I would like to do this in polynomial time. Okay. So as we will see that the polynomial time goal would be rather easy to achieve if we have the following ability, which takes me to question 3. Right, the question 3 asks, what is the probability? So maybe I should first say fix an edge E, and I'm interested in asking what is the probability that this particular edge gets picked by a random tree. E shows up in, I just want to like make sure that the first time I write this random variable, like so I want to emphasize that the red thing is random, right? The black thing is deterministic, right? And this red thing is chosen from the uniform distribution over all spanning trees, right? So I'd like to compute this probability. So your reflex should be something like this, that if I have a primitive that can solve task number 3 for me, that is for every single edge, I could give you a list of values P sub E, where P sub E is actually the probability that this particular edge gets picked by a random spanning tree. I claim that with question 3 and question 1 in your hand, you can get question 2. So like 3 and 1 kind of squeeze 2, right? So if you have a solution for this problem, if you could determine for every single edge in polynomial time in your input graph, whatever it is, that the probability that a random spanning tree of this graph picks up this edge, you know that probability value, and you also know the count of number of spanning trees in a particular graph, you could in fact generate a uniformly random spanning tree, right? So that's a claim that I'm making. Does anybody see why that should happen? It's like requires some effort. So like let's see. So here is how we will approach this goal. So I have a bunch of these edges, E1, E2, EM. Right? So these are all edges of your graph. And now what I do is that I determine the value P1, which tells me what is the probability that this edge E1 gets picked by a random spanning tree. I compute P2. I compute all the way like this thing PM, and now what I do is that I look at the edge E1, and in my mind I'm kind of building a tree. So like not a spanning tree like right now, but I'm building like this tree of decisions, a decision tree. The idea is that I'm going to toss a coin with probability of heads being P1. If the coin in fact comes heads, I'd be focusing my attention on those trees that contain the edge E1. If on the other hand, the coin toss comes out tails, I'll be looking at those collection of spanning trees that do not contain the edge even, right? So that's how this thing is going to go, right? So I mean, this is, I'm trying to like build a tree and E1 is in the partial tree, which is yet to be revealed, right? And here, E1 is not a part of the partial tree that you have built so far. Now what you do is that you come to the next node and you toss a coin for the edge E2. Okay. So you're asking, like, what is the chance that like in the tree that I'm trying to produce in this like remaining graphs. So for example, like let's make sure that so I'm going to use this primitive over and over again. So how do I compute like the number of spanning trees that contain a fixed edge? So if I have primitive 1, so like maybe this is like worth writing in a better way. So I'm saying that primitive 1, if you could solve this, primitive 1 solver implies a primitive 3 solver. So this is something that like you guys might be able to think about, like why should I be able to determine the probability that an edge gets picked by a random spanning tree if I know the number of spanning trees of any given graph? Why should I be able to do this? Complement, right? Good. So what Suraj is proposing is that he's trying to produce a new graph. How does he produce this new graph? He just throws the edge even away. Right? And now he knows that like in this graph, he could like determine, he could try finding the spanning trees of like this graph. These spanning trees do not contain the edge even. So he's looking at a ratio. What ratio is looking at? He's looking at the ratio of number of spanning trees of the graph G with edge E deleted, and the in the denominator he has all spanning trees of this graph. Right? So like in other words, what he is observing is that like note that PE for an edge E is actually equal to number of spanning trees of G minus E, I should say 1 minus PE. Right, so that's all you notice. In fact, like if you do not want to do this 1 minus business, like you could estimate P directly by looking at a different graph. So can somebody tell me a different graph where I will again look at number of spanning trees of a certain graph in the numerator divided by number of spanning trees of G in the denominator, and this ratio directly measures PE. What graph am I thinking of? What graph goes in the numerator? So there is an operation called, okay, good. So the question is that so I want to write PE as the ratio of number of spanning trees in a graph G prime divided by number of spanning trees in a graph G. The question is that what should G prime be? I want PE, the probability that this edge gets picked by a random spanning tree, to be a certain ratio. And I'm wondering if I could do this by looking at number of spanning trees in a certain graph in the numerator. So the question is, what should this graph be? Right? So the idea is you can just contract this edge. Okay. So how many of you have seen the operation edge contraction before? Okay, you have seen? Okay. Like let me just make sure that all of us are on the same page. Right? So like you have like some like big graph. What you do is that you look at this edge UV and you collapse UV along this edge into a super node. So the idea is that like this gigantic thing will become a node and it has 4 edges incident on it. Note that this process of contraction might produce loops, okay, and like that's just fine. I'll live with that. Okay. So as you will see that like my spanning tree counting process, like whatever formula it is able to handle these parallel edges as well. So like there is a lot of suspense there, right? But those questions will be answered in due time. So the idea is that if you have primitive 1, you could obtain primitive 3. Okay. Once you could obtain primitive 3, what you could do is that you can build this decision tree, right? I mean, for each edge you toss a coin, heads or tails, right? And like the coins are biased with the correct probability. So initially, like, E1 is loaded with probability P1. With probability P1, it comes heads. Now I'm going to toss a coin for E2, but the coin for E2 has to be tossed in a new graph, right? For example, suppose I'm on this branch. What I would like to do is that I would like to load the edge E2 with a new number P2, which is conditioned on the knowledge that my graph does not contain the edge E1 anymore. Because over here, I'm only looking at those spanning trees that do not contain the edge E1. On the other hand, when I'm looking at this subtree, I'll have to keep in mind that like the probability for the edge P2 has to be for the edge E2 has to be computed suitably, right? With this contraction being done. Right? Okay. So the idea is you can keep building decision tree on and on and on. And at the end of the day, you will have a legitimate uniformly random spanning tree in your hand. Right. I mean, you have a new graph, right? This new graph also has a spanning tree count. Okay. So that oracle you need to keep accessing again and again. Right. Okay. Right. So this kind of tells us that yeah, I mean, we have perhaps not asked a very bad question, and so that's one sales pitch for why these questions might look important to you. Like if your goal is to return a uniformly random spanning tree, then building primitives for task 1 and building primitives for task 3 are worthy goals. And in fact, building primitives for task 1 automatically allows you to build a primitive for task 3 as well. So let's see how we can count the number of spanning trees of my graph. I'll erase this. We don't have too many experts in the audience, so Raghuvansh, please keep the lecture grounded, right? In the sense that if, yeah. Okay, right. So, what we would do is that towards building to this goal of counting the number of spanning trees of like an undirected graph. So what we would do instead is that we would first look at a primitive that allows me to count a specific type of trees, specific type of trees in directed graphs. So let me tell you what trees I'm talking about. These trees are going to be directed, right? So we are switching over to directed land. We'll prove some results in the directed land, and undirected case will be a mere corollary. So let's see what kind of objects we want to define. So we define a divergent tree rooted at a vertex called R, right? So I mean, this is a tree kind of diverges. So there is a node R, right, and it kind of repels all the edges away from it. So the way I would say that is that, say, G is a directed graph. I will use a shorthand, I will write digraph, right? A collection of edges is a divergent tree with root R if the following conditions hold. So the conditions just tell you that in degree of V equals 1 for all vertices different from the root, and in degree of root is exactly 0, right? Okay. Right. In degree of all other vertices is exactly 1. So all other vertices have exactly one edge pointing to them. So that's an edge from the parent to that vertex, right? So, right, I mean, I think you guys are perhaps good with this. So let me just draw one divergent tree to drive the point home. So that's what they look like, right? I mean, you have some root, it kind of repels all the edges. All the edges are directed away from the root. Okay. So similarly, you can define a notion of convergent trees that I'm not going to do. All the edges go the other way in convergent trees. Okay. Now what I would like to do next is that I would like to define the notion of what is called an in-degree matrix of a graph. So let's see what this definition says. Right. So again, the setup is that G is a digraph right? And how do I define, D is the in degree matrix of G if D records the entries in the following manner, that is Dij is equal to the in degree of a vertex if, in degree of I should say, in degree of I if I equals J. So the diagonal elements just record the in degrees. The off diagonal elements, they just include negative of the number of edges from I to J. So you might say that why did I not say -1, right? I mean, so by the way, does this remind you of Laplacians? Right? Okay. So this is indeed the Laplacian. If you restrict your attention to undirected graphs, the idea would be that in an undirected graph, you would pretend that the edges are directed on both ways, right? So like you have an edge, an undirected edge I comma j really consists of two directed edges, one going from I to j, the other going from j to I, right? And if you look at such a directed graph invented from an undirected graph, its in degree matrix should be exactly the Laplacian. Right? Okay. Now you are a bit unhappy maybe because you are saying that, hey, I could have just said -1. Why allow parallel edges? So this is being done like with some foresight. The idea is that at the end of the day, I'd be trying to think about this spanning tree question where we discovered that contracting an edge might lead to parallel edges. So allowing that is not a bad thing at all. And in fact, if we can prove some theorems for this more general thing, then why don't we do it? Right? Okay, so that's your in degree matrix. Contracting might lead to parallel edges. You take an edge, you contract it, right? That might lead to parallel edges. That might lead to multiple edges between the two vertices. Right? Series of contractions can lead to parallel edges. Okay, so what do we do now? So I'd like to begin by proving a lemma. What does this lemma tell you? So the intention of this lemma is the following, that I am given some matrix D, okay, right? And somebody tells you that this matrix D is trying to capture the in degree matrix of some directed graph, okay. I'd like to understand if that matrix is in fact, if that directed graph in fact corresponds to a divergent tree. That's the question I'm asking, right? That recognize the footprints or the graph print, right? The in degree graph print of a divergent tree. Right? So let's see what that statement looks like. Let me make sure that I get that right. Yes. Oh, great, great. You're already ahead of me. Yeah. Yes. So G is a divergent tree with root R if and only if, right? So D represents the in degree matrix. So if and only if the following conditions hold about the in degree matrix. The first condition is that DII equals 0 if I equals R, right? And equals 1 otherwise, right? And the other condition is that D, I'm going to use a funny notation. I'll tell you what that notation is. Determinant of D tilde. Actually, let me use a different notation, sorry. Okay, right. So what is D minus RR? So this is telling you that look at the matrix capital D and drop the rth row and the rth column. Okay. Drop the rth row and the rth column. So maybe I will write that. This is also called depressed matrix D or reduced matrix D. I prefer reduced because depressed makes me depressed. Great. So that's the claim that we are making, and let's see if we can prove this claim. So suppose that the graph G truly corresponded to a divergent tree with root R, right? So I'm truly looking at a divergent tree with root R, okay? That's your graph. I claim that the first item here follows immediately. I will write 1 and 2. The first item here follows immediately, right? G से divergent tree root R, उसका इंटीग्रल मैट्रिक्स बनाओगे तो आपको क्या दिखेगा, right? I mean, yeah, like look at this thing, this type check. The first item just follows, right? So I guess everybody happy? Yeah. Now the second item, okay? Sorry, what? Oh, reduced matrix means that like you drop the rth row and the rth column and you obtain an n minus 1 by n minus 1 matrix, and that matrix is called D minus RR, right? Okay. So like maybe let me erase this part. I should not admit this on camera in front of Raghuvan especially, that I always get confused what is the forward direction, what is the backward direction. But I'll still write forwards. I'll pray to God that I am right. So the for concreteness, I will write that like G is a divergent tree. Then item 1 follows. Right? There are no complaints. It remains that like we should still show item 2. Okay. So like let's think about this. Yes.
We sort of say that once we remove the root, we get another root-like object in the leftover tree, and then maybe we get it.
No. Like let me draw a picture and then I'll ask a question and then you will answer this question. So this is maybe my divergent tree. I do not know why I make everybody have 2 children. Okay, sorry, but yeah. So what I'm going to do is I'm going to argue that there exists a way to permute like the rows and columns of capital D so that it becomes upper triangular. You will help me find that permutation. So for example, like this is like the maybe I do not know. Yeah, I think this is enough. Okay, so that's my graph, right? And like if I want you to find a permutation for me such that the matrix corresponding to that permutation is upper triangular. Does anyone see how can you like swap these labels around? Kya? BFS. Yeah. So the idea is like just try this labeling, man. Why don't you try that labeling? Okay. So what you will notice is that like vertex worth. So I'm going to like draw the columns of this guy also. So 1 I'm trying to. So 1 is my root, right? Right now 1 is the root, and I'm trying to draw the in degree matrix. So I know that the in degree of the root is 0, right? And like right. I mean this is. Right, and in degree of like everybody else is 1. And what you notice next is that like there is an edge between 1 and 2. So this entry is a -1, that entry is a -1, 0, 0. Like I believe you can see that this thing will be like lower triangular. I'm sorry, upper triangular. Like all the non-zero entries live in the upper part, right? And like down here, we'll have all zeros. Okay. Right. I do not know. I think that I have perhaps missed one vertex. I don't know. I think that's yeah. Okay, fine. And now you notice that like every column adds up to 0. That's a side observation. We do not need that right now. The observation so far is that like notice that there exists a permutation P corresponds to this BFS permutation, right? Such that PDP transposed is upper triangular. So I managed to find a permutation which put this matrix in upper triangular form. I'm making a side remark. The side remark is that all the columns of this matrix, they add up to 0. Do you see why? All the columns add up to 0. Why?
Yeah, definitely all the columns go to row, it doesn't get up. But I think if you complete it,
Oh, yeah, I have not completed it. Yeah, why? I mean, I'm not going to complete it. I'm also lazy. So, yeah, why will the columns add up to 0? Do you see? Like you already mentioned, Mayank.
Definition of integrity. The integrity is precisely the edges from others to you, and so integrity is positive and everything else is negative.
So this is divergent tree. Like over here, the explanation should be simpler. Okay. So the idea is that, like, this vertex, maybe like I'll pick vertex 3, it has exactly one incoming edge, and the edge that's incoming to vertex 3, so that's vertex 3, right? Yeah, I'm looking at the column for vertex 3. It has exactly one incoming edge, and that incoming edge leaves vertex 1. So the entry 1, 3, that's an entry in the third column, that's a negative 1, and there is going to be exactly one positive 1, right? Because there is exactly one in degree for this guy, right? So like these matrices corresponding to, like, divergent trees, they have this very nice property that, like, all the columns, they in fact add up to 0. Okay, so that's like nice, fine. So here is what I would like you to notice, that suppose if in this picture I drop the first row and the first column, I have a triangular matrix with ones running down the diagonal. The determinant of this thing is in fact 1. Okay, right? And now you might ask that, like, I arrived at like this matrix by a bunch of permutations, right? I mean, I'm required to think about the matrix capital D, and like I'm required to drop, like, the rth row and the rth column, whatever you used to be in the original permutation. So in the original permutation, like, you had something like this, right? This matrix, like whatever I have, it was obtained by applying PDP transposed. Right? It was obtained by applying PDP transposed, and what I'm claiming is that the determinant of PDP transposed -1, 1 is in fact 1. Right? So if I depress this matrix PDP transposed, so maybe I should depress it like that. So the determinant of this reduced matrix is in fact 1. I'd like to conclude that determinant of D with the depression being minus R and R is in fact still 1. Okay. That's something which is fairly straightforward. I would like to leave it as an exercise. Okay. So think about it back in like your home. The recording is available, so you can also look at the recording if you want to make sure you know what the question was. You'd have to be a bit careful. Essentially, what you would discover is that like this determinant is equal to determinant of D with the depression minus R and R with QQ transpose, two different permutation matrices applied to it. So you could find a different permutation, right? The idea is that, like, the permutation matrix like which goes here corresponds uniquely to a permutation matrix that you could, so the idea is that this determinant exactly equals the determinant of D with depression minus R comma R flanked by two permutations Q and Q transposed. Great. So that's the forward direction. And now we still need to do the backward direction. So in the backward direction, what you are told is that like you are given this matrix D, you are told this matrix D satisfies item 1 and item 2. You would like to conclude that this thing in fact corresponds to a divergent tree. So we are told that the matrix D satisfies items 1 and 2, and you want to argue that want to show that G is in fact a divergent tree rooted at R, that R which was reduced, right? Yeah. So that's the claim that you would like to show. Okay. So the idea is to proceed by contradiction. So suppose not. Suppose G is not a divergent tree, but I know something. What I know is that everybody has in degree 1, right? D was supposed to be an in degree matrix, so everybody has in degree 1. So what this means is that since this is not a divergent tree rooted at R, then there exists a vertex in your graph that R cannot reach. Because think about this, that there is this vertex V, it has in degree 1, right? I know that G is not a divergent tree. If it was a divergent tree, R would have reached everybody, right? So what must happen is that this thing closes off into a cycle. This way. Right? So you get a cycle, and this entire cycle is not reachable. This is a cycle capital C. So what we have discovered is that note all vertices in capital C are not reachable by the root. Okay, so that's kind of like nice. So maybe I can try the following. So what I will try is I'd like to order the vertices in the following manner. To get a block diagonal form is what I want to get at. So the idea is that there is a bunch of people reachable from R who kind of live over here. All the vertices in capital C, they live in this part, and you have a block of zeros, right? I mean, you must have a block of zeros because I'm not supposed to reach any of those, right? So the root lives in this block, right? R lives somewhere over here, right? So R can reach a bunch of vertices. R does not reach the vertices in capital C. So whatever your divergent, whatever your in degree matrix is, after some permutations it can be brought in this form. After some permutations you can bring this matrix in this form. Okay, so what do I do now? So I observe that you are told that this determinant, the depressed determinant, is in fact exactly 1. The depressed determinant is exactly 1. So what you can conclude is, so let me just make sure that I get one detail right. Sorry, yeah. So I want to drop the rth row and the rth column. So I drop this thing, right? And next I note that all column sums in C. So yeah, that's the observation I wanted to make. So look, I mean, I know that all columns, they add up to 0. This part is already 0. So all columns of C, like these guys, they also add up to 0. This tells you that the determinant of C is in fact 0. But I note that this is a block diagonal matrix. Determinant of D minus RR is a block diagonal matrix. So its determinant is determinant of this piece times determinant of C. So determinant can't be 1. Right? So that's a contradiction, right? And that allows us to conclude that in fact D is a divergent, corresponds to divergent tree. So, but we know this matrix D minus RR is block diagonal. So this implies that the determinant of this depressed matrix is in fact determinant of, like, I will call that the top piece times determinant of C, which is 0. Okay. So that wraps this thing up. So that's nice. Okay, good. So, sorry?
Let's say the vertex is reachable,
Mhm.
but it is still not a divergent.
Oh, no, but then, like, look at the conditions that you are given, right? The conditions tell you that everybody is in degree 1. Okay. Everybody is in degree 1.
So is that part of the reverse implication premise?
I'm sorry?
So the reverse implication would just be that I have a matrix with so and so properties with the properties that that the graph has in degree 1 and sorry, every vertex has in degree 1 and there's some vertex that has
Okay, good. So are you asking?
part of the reverse implication.
So let me make sure that I understand your question. Are you asking that, like, if everybody is in degree 1 and the root can reach each and every vertex, then are such graphs legit divergent trees? Is that what you are asking?
No, what I was asking was your first statement was let G be a graph, be a divergent tree such that everything except R has in degree 1, R has in degree 0. And then your second statement was determinant of matrix with the R is row and R is column removed is 1. So for the reverse implication, I thought you should only have the fact that like the R is row and R is column removed should be 1. Okay.
I mean, I think I missed your question still, but I think it's answered. Okay, I'm sorry. Did you catch the question, Raghuvan?
I think so. So the actual statement is somewhat like this. I believe so. For any graph G, define a matrix P,
In degree matrix.
Then for any graph G, P of G has those properties that you know they.
Oh, it's fair.
Okay. Yes.
Not a mention of divergence G is arbitrary. What's the definition of the divergence G to that? This is an integrity condition.
Yeah, this is the degree condition.
Why not this satisfy the integrity?
Oh, okay. So I mean, why does this not satisfy the degree condition? Sorry, what?
The integrity condition and connectedness from R is also there.
Yeah, I think perhaps I should emphasize that. So that's my bad. Okay, so what do I want to do now? Yeah. So what I'd like to do next is that I'd like to tell you how you can count the number of divergent spanning trees rooted at any vertex R. Like, we'll discover that, like, no matter what root vertex you pick, this quantity is going to be the same. It's going to be like exactly one value. Okay, and so that's a very interesting claim. Oh, but one thing that, like, one should mention is that like, from a distance it kind of looked like an ugly task, right? I mean, trying to determine from the n-degree matrix whether this n-degree matrix corresponds to a divergent tree, but, like, lo and behold, determinants can be computed in polynomial time. Therefore, this task can also be done in polynomial time. Recognizing whether D corresponds to divergent tree, it can be done in polynomial time. Right. So next up, what I would like to do is I'd like to prove the following theorem, that the number of divergent spanning trees at R.
So essentially, the determinant is one that it is a divergent tree just rooted at some other vertex.
I'm sorry, I did not understand your question. What are you talking about?
Like, if the determinant is, let's say, 1, but you remove the R and row and R is column.
So the row and column that you get rid of, that's where your divergent tree is supposed to be rooted.
Yeah.
Right? Yeah. That's where the divergent tree is supposed to be rooted, because
it will be a divergent tree only if the determinant is that just imposed by the matrix.
so So like whatever the root is, if you look at the column,
column thing you remove, that should be removed.
yeah.
Are you saying you do this operation, you remove some A from a column, row, and then you get it?
So look, the root is important for us. When we are trying to talk about divergent trees, it's important that they have a root. And the idea is that, like, if you look at the column corresponding to the root in the matrix capital D, that column is in fact all zeros, right? So this matrix viewed as a whole is clearly singular. Okay. So what we are trying to say is that, this singularity can be removed by kicking off a specific row and a specific column. Which row and which column do we kick out? So the row and column that we kick out is like precisely corresponding to the root, right? We get rid of this zero column, right? So
This direction, one way going backwards. We don't need the first condition.
I'm sorry.
Can we just do this backward condition using only the second condition?
The backward direction using only the second condition. No, I mean you need reachability. You need reachability. Right? The first condition is just an in-degree condition. So I guess what you are asking is that if my graph is kind of like, let's say, just like this. So like, hold on, I'm trying to like make sure. So if this is my graph, right? I mean, does this satisfy the in-degree condition? Does the 6 vertex graph satisfy the in-degree condition? That's the question that you are asking. So like, everybody is in degree 1. Everybody is in degree 1. Root is supposed to have in degree 0. Right? Root is supposed to have in degree 0. So this specific instance does not satisfy the condition that I wanted. Right, so we'll go to this theorem. So the claim is that the number of divergent spanning trees rooted at R, its determinant of D with the rth row and rth column removed. So yeah, like let's prove this claim. We will see later that, like, so you want to compute the number of divergent trees rooted at 1, it's some number. You want to count the number of divergent trees rooted at vertex 2, that's some number, some different determinant of a different matrix. So all of these things look like determinant of different matrices, all of which are kind of related. They are related through the right hand side, right? I mean, the right hand side matrix is fixed. Which row, which column gets kicked, I'm sorry, the right hand side matrix corresponds to the underlying graph, right? And like the row and column that gets dropped from this matrix, like, that is really depending on which vertex you want to make the root. So the idea is that all these numbers from a distance, you might think that they are different, but they are really not. We'll show that in the second claim, right? So here I'm going to assume that you're rooting everything at the first vertex, V1, right? And all columns add up to 0. I want to draw a picture. So, but yeah, so first I will draw this thing. So this is like maybe the matrix capital D, which has a bunch of zeros in the first row. Then some entries over here. I do not know what these entries are. Right? And here you have the rest of the matrix. I'm calling it rest of D. I think you know what I mean. Right? The remaining graph, the remaining entries are loaded over there. Okay, so what I would like to do is I would like to give you a new matrix. So what is this new matrix? So D new, I put a copy of E1, the standard basis vector E1 in the first column, right? All the remaining entries. So I'm talking about this matrix capital D, right? So given you want to show this theorem. So in order to show this theorem, I'm saying that let's show this theorem only when the root is the first vertex.
What is the graph?
It's a general digraph. It's a general digraph. It's a general digraph. Yeah. I'm sorry. Sorry. So yeah, I mean, like let's see. So I mean, the idea is that if you look at Dij, what does Dij represent? Dij represents, like, the number of edges from, so Di1 I'm looking at, number of edges from I to 1, and that quantity is in fact 0. right? di1 is 0 for every I. Oh, so it's a divergent tree, right? I mean, so the idea is that, oh, it's, I'm sorry. I'm sorry, yes. Just one moment. Yeah, that's a good point, right? Yeah, so what I'd like to do, okay, just one moment. Yeah, it's a general graph, you're right. Okay. So this thing I can't be certain. Yeah. Okay, so there is like some column, like there's some entries in this column. I do not know what they are. The only thing that I know is that like all the columns, they add up to 0. Right? All columns, they add up to 0. So what I would do now is that I would define a new graph, a new matrix, d new. In d new, the first column is this vector e1, and I have the rest of d over here. You just copy over the rest of d. The idea is that determinant of d new is in fact exactly equal to the determinant of d with the first row and the first column removed. Right? Determinant of d new is exactly this determinant. So that's what I wanted. That's like all I wanted. And now let's I'd like to demonstrate what this proof looks like via a picture. So let me make sure that I get that right. Oh, so all I did is that I replaced the first column. Whatever the first column is, just replace it by the standard basis vector E1. Okay. So the idea is that at the end of the day, I am anyway going to evict, I am going to remove the first row and the first column. So what am I looking at on the right hand side? I am looking at determinant of D with first row and first column gone. So I might as well look at this matrix. And now for the rest of the argument, I am going to work with D new. Right? Going to work with D new, and that's like really what's going on. So here is a graph G. So this, by the way, I took from the notes of Gary Miller, this example. So the idea is that I have this graph. Okay, and dg for this graph, whatever it was, I'm sorry, I think I should write d new for this graph, whatever it was, it has 1 0 0. Then like look, the vertex 2, its in degree is 2, right? Its in degree is 2. Okay, so just to make sure that like all of you can see this and that, right? Vertex 2 is in degree 2. And the columns add up to 0. So I have vertex 3 is in degree 2, right? I mean that also you can see this edge and that edge. So okay. What I would like to do is I'd like to use the lemma that we just proved. Okay. So towards using this lemma, I would like to persuade a matrix to appear. I would like to persuade in the rest of the analysis the matrix corresponding to divergent tree to emerge. Right? So this I do by looking at whichever things there are 2's on the diagonal or things bigger than 1 on the diagonal, I want to split it off. Right? I want to pass on to smaller and smaller graphs. So for example, over here I can pass off to these graphs G1 and G2, and I can tell you what matrix I'd be looking at. So this thing becomes a 1 plus 1, negative 1, 0. So what I'm doing is that I'm trying to preserve this property that the columns, they continue, the column sums continue to add to 0. That's the property that I am preserving. Of course, ignore the first row, I'm trying to preserve this, ignore the first column, I'm trying to preserve this property of columns adding up to 0 for the remaining columns. Right, so over here the column does add up to 0, and you perhaps know what I'm doing, right? I mean this is the matrix D1, this matrix is D2. I'd perhaps like to draw that graph too. So, and I'm terrible, so maybe somebody can help me understand what these graphs look like. think that's the graph corresponding to which, like, D1 will be the in degree matrix, right? And then I have this other graph. Right. So you perhaps remember from your linear algebra classes that determinants are multilinear. So if you split off a column as a sum of two separate column vectors, what you would have is the determinant of d nu will be the sum of these determinants, will be the sum of that of d1 plus that of d2. Right. The remaining idea is to continue recursively. Okay. Continue this process recursively. So if you continue this process recursively, for this specific example, like, I will like just draw a few more things. So for example, for D1, what you would like to do is you would like to split D1 off into two more graphs. Okay. Only if those graphs correspond to a divergent tree will you get a contribution. The contribution will be +1. Otherwise, the contribution is 0. Right? So I'm going to continue this process recursively. So let's see what another step of continuing this process recursively looks like. What graphs do I get? Right. So like maybe I will split off like this graph. Sorry. Kya?
Third column is
Yeah. Third column is the column that I'm going to look at to split D1 off, and like third column is what I'm going to look at to split D2 off. So like so for example, like I'll just quickly like draw without I'll draw the graphs corresponding to G1. So maybe I'll draw without telling you. So this is what those graphs look like. So they both contribute 1 to the determinant. Right? So these things, they contribute 1 to the determinant. But when you split G2 off, you get digraphs that look like that. Right, so you get a contribution of 0 from here. But I hope that the general idea is clear, that what this process is doing is that it's recursively trying to break off a column where the diagonal entry in that column in this matrix is greater than 1. Right? What you do is that you just split it off recursively. Right? You preserve this property that the columns, they are required to add up to 0. Right? While respecting this property, what you discover is that you have broken your graph into like some subgraphs, which you can continue splitting off recursively. At the end of the day, the determinant splits off as a sum of determinants of a whole bunch of matrices, of like a truckload of matrices. And the entire idea is that all of the final matrices that you end up with, which correspond to divergent trees, they will contribute 1, the others will contribute 0.
because the column sum is
So because you are also doing this reduction thing, right? This determinant of right. I will not say because columns sum to 0, because of like that lemma that we just showed. So remember the lemma that we showed. That lemma used to assert that if your matrix is an in-degree matrix corresponding to divergent tree, its determinant is in fact 1.
that is good. Why the others are 0 is not very.
Why others? Oh, the other thing. Yeah. The other things. Okay, right. So what you're asking is that if my graph does not correspond to a divergent tree, but it has this property that like all the in degrees, right? I mean the in degree condition is okay. So let me make sure that I write what your question is. So remember, I mean, what our like lemma used to assert. That lemma told you that if your the graph G is truly a divergent tree, then there is some suitable conditions that hold true for the in degree matrix, and those conditions used to tell us that DII, the diagonal entries, they are once everywhere except at the root, right? And the other condition told you that the determinant of the reduced thing is 1. If your graph has a bunch of entries So if the n-degree matrix corresponding to your graph has the property that it does not truly correspond to your divergent tree, but all entries are 1 or 0, right? All entries are only 1 or 0, right? Then okay, so let me.
The integrity condition is satisfied, but the determinant condition is not satisfied.
The depressed determinant condition is not satisfied. I'm just wondering what. Yeah, it should be 0. That's what I'm claiming, and I'm just wondering if I can think of a quick proof why. Raghuvansh, can you help here? Okay, so the question is that you are given this condition that so what are we doing? We are trying to count the number of divergent trees rooted at a particular vertex by looking at by expressing the determinant of d nu as a sum of determinants, and the hope is that these determinants will contribute 1 only if they correspond to a divergent tree. If they do not correspond to a divergent tree, why is it clear that they contribute 0?
I thought the answer would be that you will keep splitting this till you get to see that only have n minus 1 levels.
Yes.
You only have n minus 1 levels.
Oh yes. 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 Yes.
If it's not a divergent tree rooted at R, then maybe you necessarily have to correct it.
If it's not a divergent rooted at R, exactly like what Raghuvan said, you will have a cycle. You have n minus 1 edges, you have n minus 1 directed edges, right? And there is like a cycle sitting somewhere, and the entries in that cycle, they will add up to 0. So if you look at the submatrix corresponding to cycle, it will add up to 0. Yeah, it's the same thing that happened here. Sorry. Okay. Right, so I have half an hour more. So what I'd like to do first is that I'd like to argue that all of these determinants, so I took a divergent tree, like I counted the number of divergent trees rooted at vertex 1. I counted the number of divergent trees rooted at vertex 2. On and on and on I went. Right? And I wanted to argue that all of these things, they're really the same. Okay. So how can I argue this? So let's argue this. So this will become clearer in the undirected case. So let's see. Right. Yeah. So I want to take you to the undirected case. Right, and the idea is that in undirected case, what you do is that you bidirect all the edges. Right, you put directions both ways. So what you have is the n-degree matrix of G with directions directed both ways. That's exactly equal to the Laplacian of the graph G. That's exactly equal to Laplacian as we discussed at the very beginning. Right, and now the claim is that take any root, and now you have that the number of spanning trees of this undirected graph G is equal to the number of divergent spanning trees rooted at R. I claim that you can give a very clean bijective proof for this. Does anybody see that? There is a very clean bijective proof. Very direct. Right? So you take some arbitrary root. You want to count the number of spanning trees of the undirected graph G. I am claiming that this collection of all spanning trees of this undirected graph, these undirected spanning trees, it's in bijection with the collection of all divergent trees rooted at R. This is a clean bijection that you can give.
So you take any spanning tree, let's say R is any vertex, and you, since it's a spanning tree, you just going outside.
That's the bijection. The bijection is the obvious one, right? I mean, I'm giving you T, I'm giving you R, and you know what to do. Like R just repels all the edges away from it. Right? So these two sets, they are in bijection. So I'll just say that proof is obvious. But this means something. This means, as a corollary, that if you count the number of spanning trees of an undirected graph, what you could do is that you could look at the Laplacian, you could eliminate any row and any column, and done. Right? So eliminate like the same row and the same column. Right? Remember, Laplacians are singular matrices. Their determinant will come out to be 0. So the corollary we have is that the number of spanning trees of an undirected graph G is exactly equal to the determinant of this theorem is called the Kirchhoff matrix tree theorem. It's the electricity wala Kirchhoff. Right? He discovered this theorem in 1847, like 100 years before like we got independence. And he was a 26-year-old and he was not even interested in counting the number of spanning trees. He could be least bothered about it. But he was like really in that paper itself, he laid down the foundations of modern electrical network theory. It's an 8-page paper written in German, so of course I can't read it, but there is a thesis of this person called Fabian Holzer. Like it converts that thesis and like extends several results in like modern language. I'll highly recommend it. So I'll just write the name for you, Fabian Holzer. So now in the remaining half an hour, what I would like to do is I'd like to chase this question. I just do not know where I'm going, right? I mean, I'm trying to put on the hat of somebody who is trying to discover the expression for probability that an edge gets picked by a random spanning tree. We already know how to compute this probability, but we also know right now how to compute, how to return a uniformly random spanning tree. We just do that like branching process we discussed earlier. We could discover for every single edge the probability P sub E that edge gets picked by a random spanning tree. And I will use that oracle over and over again like you mentioned, and I can get algorithms that return a random spanning tree. That algorithm is kind of slow. You need to invoke that oracle multiple times. Every call to that oracle involves determinant computations. We don't like it. We would like to speed it up, right? So one way to speed it up, as it turns out, we'll go by a very indirect route. The indirect route is that first we compute the probability that a particular edge shows up in a spanning tree. We will try to write it in a manageable way. We'll try to get insight from it. But let's see, let's just chase a specific goal. The goal is to compute for a fixed edge E the probability that edge gets picked by a random spanning tree. I call this probability the desirability value. Right? I mean, the idea is that it measures how much is this edge desired by a random spanning tree. So for example, if I have this graph, I have a clique on n over 2 vertices, another clique on n over 2 vertices. The two of them are connected by a single edge. The desirability of this bridge edge is what? The desirability of this edge is 1. It must show up in every spanning tree, right? So, yeah, fine. But desirability is a very global notion in the sense that how much desirable this edge is. Like in order to determine that, I perhaps need to look at the entire graph. It does not appear to be a very local property, right? I mean, it seems I have to examine what's going on in an entire graph. Kind of looks ugly, but still, let's see what we can do. So the question is, again, I have fixed edge E. What is the probability that this edge shows up in a random spanning tree? I'm not let me write once more, uniform from all spanning trees. It just becomes too big, too unmanageable. Okay, I'll drop this thing below from now on. Fine. What we will do is that we will just chase our nose. We will see where our explorations take us. We'll end up with a quadratic form. The quadratic form we were going to end up with will be a quadratic form computed with respect to a PSD matrix. And that will be a point for some detour motivated by physics. But let's just compute this probability. So I'm going to switch between some notations. So instead of writing L minus RR, so I will often write L tilde. That's just some notational switch, right? So here is an attempt at solving this problem. So the attempt is something like this, that let the edge E be called I comma j, right? And Suppose alpha E denotes the probability that the edge E gets picked by a random spanning tree, right? So you can write alpha E as 1 minus the probability that this edge does not get picked by a random spanning tree, right? And this expression you could write as a ratio of determinants, right? Determinants of like which matrix? Let's see. So this is determinant of L minus BE transposed tilde over determinant of L tilde, right? You remember what B tilde is, right? So like the edge E, I dropped it from the graph. So I have to look at the Laplacian of the graph with edge E removed, and the Laplacian of the graph with edge E removed corresponds to dropping the mini Laplacian from the edge E, and mini Laplacians, if you remember, BE was this vector 1i minus 1j. In other words, the mini Laplacian for the edge E, LE, is just 1i minus 1j outer producted with itself. And this vector has a very specific pattern of plus ones and minus ones, right? Plus ones on the I diagonal entry, negative ones on the cross diagonal entries, on top diagonal entries. Okay, so that's the expression I'll get. Now, I claim without proof, that I will prove later, that this expression is equal to, so this is what is called the Sherman-Morrison formula. Sorry?
This is what we did in first 10 minutes as probability.
No, we did not do this part. We did not do this part. Yeah. Yes. Right. So, like, you're dropping, like, some particular row and particular column from this guy. So I claim that, like, you could also write it two tildes, right? Dropping the same row and the same column. Okay. So what the Sherman-Morrison formula says is that if you apply a rank 1 update, this is a rank 1 update. I am adding a rank 1 term to a matrix L tilde. So what the Sherman-Morrison formula says that if you have got a non-singular matrix, capital A, and if you add a rank 1 perturbation to it, the determinants change in a very predictable way. So what's the new determinant? So, like, as I'm saying, I have not proved Sherman-Morrison formula yet. This is exactly equal to determinant of L tilde times a scalar. It has to be a scalar. So what's that scalar? So it's 1 minus BE tilde, right? So this is like, you look at the vector BE and you drop, like, let's say the ith entry. So we are dropping the ith entry everywhere. So the entry that we are dropping is exactly the ith entry, let's say. So I should write II. Right, BE tilde, L tilde inverse, BE tilde over determinant of L tilde. Right, so this is like, these things cancel off. So maybe I like to do that cancellations, and what you end up with is a quadratic form, BE tilde transpose L tilde inverse BE tilde. That's some expression, some weird expression. So the last step is the previous. Oh, I did not explain this. I'm saying that the mystery hides in Sherman-Morrison formula. I have not proved the Sherman-Morrison formula. I can write the state. Sorry?
Sherman-Morrison will be the inverse. It's determinant of a rank.
But it belongs to the same family. Yeah, it's a simpler thing. But I'll show the proof also. I'll show the proof. We are going to fine. So I'll do the proof, but like, I just want to like make a few comments. So the mystery hides in Sherman-Morrison formula, which I will prove in a bit. I want to just make a comment that so Piyush is here and I'm on the record, so like, I might as well say some controversial things. So, this is a quadratic form. I claim that this quadratic form is being computed with respect to a PSD matrix. Okay, that part is not controversial yet. Okay, whenever physicists look at quadratic forms with respect to a PSD matrix, they get balle energy. So, quadratic forms computed with respect to a PhD matrix, physicists like to think of that as an energy, some kind of energy. So you might be interested, why is L tilde inverse PhD? So hints for you, how many of you have heard of the interlacing theorem, the eigenvalue interlacing theorem? Eigenvalue interlacing, anyone? Okay. Eigenvalue interlacing. So you take a PhD matrix, add a rank 1 update to it, okay? The eigenvalues of the new matrix, I will call it mu1, mu2, mu10. Of the old matrix, I will call it lambda 1, lambda 2, lambda 10. You have lambda 1 is less than equal to mu1, is less than equal to lambda 2, is less than equal to mu2. So the eigenvalues interlace. Okay, that's pretty remarkable. Yeah, like I think of that as a very cool theorem, right? So the idea is that eigenvalue interlacing will tell you why L tilde inverse has got to be PhD. Okay. L tilde inverse is PhD. That's like I'll also teach this in our regular course hours. So I don't want to spend time proving for you why L tilde inverse is PhD. It's not such a bad proof. The reason, I mean, so L tilde is PhD, right? Okay. No. Okay. So that's an easier argument. What Piyush is saying is that look, L tilde is a principal minor of a PhD matrix capital L. Therefore, L tilde is PhD, and therefore its inverse is also PhD. That's a better argument. That's a better argument. Yeah, I mean, that was the argument that I hacked up for my notes, but now I'll use yours. Okay, right. So L tilde is PhD, L tilde inverse is PhD, and this physicists claim look like energy. So let's try to imagine why, how can I make this analogy sharper? This is, but Piyush, you have seen it. This is V equal to IR, but Piyush, I am the one giving the lecture, I dispute that. I dispute that. Right. So, I want to build some intuition. In what sense, in what justifiable sense do you call it energy? So, the temptation is huge. The temptation is to immediately connect it to electrical networks. Right. I mean, dono jagah graphs hi bante hain. Right. But let's see in what sense can you make that analogy precise. So, the idea is I'm going to draw some graph that I do not know what I'm drawing. And there are what I would like to do is I notice that L of x plus alpha times 1, alpha is a scalar, is the same as Lx. तो कहानी क्या चल रही है देख करके ऐसा लग रहा है कि if I interpret as x as a vector of potentials x1, x2, x3, x4, x5, xx, right, and these things as resistors. So unlike Piyush, I am a bit skeptical when I look at these things. I am like कि पता नहीं है कहाँ फटेगा, will it work, will it not work, is this transformation valid? It is valid, as we will see very shortly. The idea is that, sorry, that's the history, but here I don't like the history. I don't like that. I don't like that. Yeah, but I don't like it. Yeah. So anyway, the idea is that अगर मैं इसको resistor के जैसा treat कर रहा हूँ and then I am trying to compute the currents that go through this circuit. So the idea is if I shift the potentials, it does not matter. And so far, one sanity check passes as far as I am concerned. I'm like, okay, I can perhaps believe that the physical interpretation is correct, but let's make sure that the physical interpretation is in fact correct. So the idea is something like this, that I start out by writing Lx equals B. Okay, B क्या है, right? So from all vertices of the circuit, I am trying to pull out some current. यहाँ से मैं कुछ करंट एक्सट्रैक्ट कर रहा हूँ. Current is going in some crazy direction. Right? So the idea is that if you look at what's going on in the jth entry in this computation.
They make a quantity that this imply that for this equation that some of the ends of gas which again is the current is coming in.
Yes. Sure. You're absolutely correct. But yeah, let me just try to tell this to the class. So imagine that I have a vertex j, its degree is 4. So the idea is that if you look at the matrix vector computation corresponding to the jth row, so I am multiplying the jth row with all of x. So what you will see is something like 4xj minus, I do not know, I will call it a, b, c, I, 4xj minus xa minus xb minus xc minus xi equal to bj. So the idea is that I can write this as xj minus xa plus xj minus xb plus xj minus xc plus xj minus xi equal to bi. And that kind of looks right, because like what's happening is that I'm imagining that all these resistors have resistance 1. Okay, I've applied like some potential drop. The potential drop across the endpoints of this edge is xj minus xa, xj minus xb, xj minus xc, xj minus xi. Whatever the excess is, that goes along the this bj. Right? So the excess is pulled along this wire bj. Right? Okay, good. What I'd like to do now is I'd like to give this perspective, which is obviously very clear to Piyush, unless I goof it up, that like what do these electrical computations look like when you work with L tilde? Okay, so I'm trying to think about L tilde, and I'm trying to think what do these electrical computations look like when, in fact, like L tilde is the matrix of concern. So the other comment I would like to make is that if you compute X transpose Lx, that in fact computes the energy of this circuit. Right? So let's see what do these computations look like when L tilde is involved. So the idea is something like this. I often draw the batteries wrong, so now I'm going to draw batteries. Yeah, I might as well use this picture. Right, I will call that xj, the jth vertex. This is the ith vertex. Right, and I'm trying to connect up a battery. And the idea is like something like this, that the voltage of I, xi, I'll think that it has been pinned to 0. So when you look at L tilde, where L tilde corresponds to L with the ith row and the ith column removed, okay, what is happening is that like this vertex I is essentially grounded. Okay, I mean, like potentials, you could shift it by anything, so I might as well shift the potentials to make sure that xi is at 0 potential. And I can do computations with respect to like this situation. So what I would get is that xj minus xi becomes like this thing, and like suppose that the like vector I'm looking for, the vector b on the right hand side, the vector b is in fact like I don't know, ej minus ei. Right? So if you look at b tilde, that's just ej, because like this it is a vector with one fewer coordinate. Recall b tilde lives in Rn minus 1. So what's happening here is that this sum I discover, it equals right. So I'm looking at what? I'm looking at the jth entry, right? So the jth entry is 1. Right? So this thing is in fact 1. So that's the expression that I will end up with. Right? So what I'm saying is that I have hooked this battery. I am pushing 1 ampere of current on this wire. I'm pulling 1 ampere of current on this wire, and like I'm trying to examine the effective resistance of this circuit. Right. So the idea is that so I have L tilde inverse facing off against the B tilde E, that L tilde inverse BE computes the vector of potentials. Assuming xi equals 0. This thing is in fact grounded. Right, so what I would like to do is that I do not really like L tilde. I'd like to massage this expression into an expression that I do not hit as much. That's a personal quirk. I hate this expression because I really hate looking at minors and the inverses of minors. So we'll try to massage this expression into like a form that is at least more palatable for my taste. So what I would do is that I will define a new matrix. This matrix I will call it capital K. Capital K is also supposed to be an inverse operator. Capital K is supposed to mimic L tilde inverse. Okay. So capital K is this matrix. It's L tilde inverse, 0, 0 transposed. And then I have a scalar. Scalars I will write in green. 0. The idea is that instead of looking at B tilde E, I can look at BE. So what I have is that BE transpose KBE is in fact exactly equal to B tilde E transpose L tilde inverse BE, which was the expression I had over here. So that's what this expression looks like. Okay, good. So what am I trying to do here? So let's see. Oh, okay. So like, I mean, the idea is that, like, in L tilde, what was happening is that like you removed the ith row and the ith column. So this is the same effect as like, marking xi, choosing xi to be 0, and then you like do the remaining computations. So for example, this is the situation you would imagine when you work with the matrix K instead. Right? Oh, okay, okay. So the idea is that, like, you're solving Lx equal to B. X is the vector of potentials, B is the vector of excess currents. Okay. When you put L inverse on the other side, you are computing the vector of potentials. Yes.
So the standard data, the x minus that should be minus the amount of current taken out because like current goes from high potential to low potential.
I mean, so like some of these things might be negative. I don't know. Right. Oh, sorry.
Current is taken out. So it should instead of current taken out.
Oh no, so I'm looking at it like this different picture now. So earlier I was looking at the picture with respect to like capital L, where I had wires coming out, and the wires were carrying excess currents, right? Where these excess currents could in fact be negative. The vector B was an arbitrary vector.
Sign convention. But yeah, so with the right sign convention, it will work.
If you use the right sign convention, it will work. Yeah.
When we remove the ith row and ith column, we are kind of removing the existence of vertex I itself. So like we should remove the
Yeah, the vertex I is gone. The vertex I is gone. You're right.
we should remove the edges.
No. So what I'm trying to like do, so what you're trying to say is that why don't I throw away vertex I altogether in this graph? Right? You're trying to say that why don't I throw a vertex I altogether in this graph? So I'm saying that as far as solving linear systems is concerned, right, with L tilde, so what I'm telling you is that, like, okay, so I should have perhaps written B tilde I over here, right? So what I'm claiming is that the vector of potentials that you obtain, like, that can be inspired from this picture. So the idea is that, like, I'm setting xi explicitly to be 0, and I'm trying to compute the remaining potentials. So the idea is that, like, if you compute Lx with the xi being 0, so xi hits the ith column anyway. So that thing that gets zeroed out. Yeah, that does not hit the ith row, that's sure. Just 1 moment. Yeah. Okay, like, I mean, I guess that I am kind of putting myself in tangles by Piyush, like, any suggestions here?
I would just say that suppose we have we are trying to solve that problem. Like there is some resistors on each edge, and we are trying to just see the voltage along some ij pair for a given current or the other way. So this one, like we're trying to find the voltage given the current. So it's the current source is the current current. Now in right hand plane, this is like exactly the fashion. But you notice that they are not linearly independent because L is the all one vector is.
Always vectors in null
And
space.
this thing of throwing away one equation is very natural. So that's where this minor is coming. So you cannot use all the equations because they are not actually. So,
There is linear dependence in your system, right? So you throw away one equation.
right,
That's what he's saying.
that's why you throw away one. Yeah, that's why you have to throw away one. It doesn't throwing one is enough. So this actually you have done many times from first year solving these circuits. But this is exactly that process. So that difference is also sort of the right hand side because some V has to sum to 0. The current entering the circuit has to be the same as the current going out. And why is that? Because when you write out check like Alex equal to G, one is in the null space of L, right? L is symmetric, so that shows already that one transpose of G is
So like perhaps like
then this L theta also shows up. Yeah. So then this idea, the idea you have to go to a minor. It's like the more abstract version of symmetry. You cannot use all the equations. You have to.
so like I mean in the interest of time I will do two things. So first I would claim that like I was trying to show that this thing is exactly equal. This thing is exactly equal to the expression in black, which is BE transpose. I lose the tildes. BE transpose times L pseudo inverse times BE. It's trying to take you to this conclusion. This is why I was trying to go through this like entire route. That like I can throw the tildes away. Like for me, this thing. Sorry, this is L pseudo inverse. L pseudo inverse, not Hermitian.
L is not invertible.
L is not in Laplacians are not invertible, right? So
But a pseudo inverse is very
L pseudo inverse is something like this. It's 1 over lambda I times UI transpose, where UI is so this is for like so it inverts the action of L on the subspace orthogonal to all ones. Inverts so anyway, so like here are like the major steps that I want to like recap. So step one is that what we showed is that the probability that the edge E belongs to T was exactly equal to BE tilde transpose L tilde inverse BE. Step two that we had was to argue that like you know this expression that we had BE tilde transpose L tilde inverse BE is exactly equal to an expression where I can throw the tildes away. So it's exactly equal to that expression. And the third step tries to massage this into a yet another form that I find a bit illuminating. Right? BE transpose L dagger BE is exactly equal to the maximum value over the subspace orthogonal to all ones. It's max over all vector 6 in that orthogonal subspace of the quantity x transpose LEX divided by x transpose LX. I am going to assume that steps 1 and steps 2 have been done. Step 1 was done, right? You saw that up to skipping the Sherman-Morrison. It depends on, it's LE, right? So this step I will prove. It has a natural physical interpretation that like, you know, how much desirable should an edge E be for a random spanning tree, right? It kind of corresponds to the maximum fraction of energy that the edge E consumes, right, relative to the energy dissipated across the whole circuit. Okay. So that's something that I will prove. Step 2, like I was trying to get through that, but did not do it in a like way that at least I like, but I have more time. This is an extra class, so yeah. What I will do now is that I will prove Sherman-Morrison for you. Okay, and then like we will go for a break. I'll prove the Sherman-Morrison formula and then we'll go for a break.
What exactly are you trying to prove this theorem?
Right, so we were trying to think about generating, so maybe like let's take that question offline because there is a lunch time, right? So I'll be coffee time, so yeah. I'll just quickly prove the Sherman-Morrison formula. And as Piyush says, it's perhaps not Sherman-Morrison, but fine. Then the determinant of a rank 1 perturbation of A is actually exactly equal to the determinant of A plus V transpose A inverse U. That's the claim that we would like to show. So in order to build some intuition towards this claim, it's good to understand what happens when A equals identity. So consider the case that A equals the identity matrix. So what do you have? You are looking at identity plus UV transpose. Iska determinant dekhna hai. This nonsense is exactly equal to the product of all the eigenvalues of this matrix, determinant of, lambda I of I plus UV transposed, right? That's what you're trying to think about. You're trying to multiply all the eigenvalues of this guy and you're trying to see what that expression equals. So the idea here is that like let's try to think कि इसके eigenvalues क्या होंगी. Okay, so I claim कि like you know I plus uv transpose को अगर u से मल्टीप्लाई किया जाए तो क्या होगा? This is equal to u plus u times uv transpose. I'm sorry, u plus v transpose u. Right? This is u 1 plus, so I'm factoring u out, v transpose u. Right? मतलब u एक eigenvector है. Right? U is an eigenvector. Okay? U came out parallel to itself. So maybe I will write u in red here. Okay? U एक eigenvector है. और u के corresponding जो eigenvalue है, that eigenvalue is this scalar 1 plus v transpose u. That's the eigenvalue that corresponds to this guy. Now, what are all the other eigenvalues? कोई भी और eigenvalue उठा लेते हैं, ठीक है? एक eigenvalue तो मतलब भैया 1 plus v transpose u हो गया. I claim the remaining eigenvalues are still 1. Why? Rank 1 update. Right? It's a rank 1 update. All the other eigenvalues are 1. All other eigenvalues equal 1. So what this means is that I'm sorry?
If you argue a little bit more, I mean, if you put it for identity, otherwise it's not work.
I'm sorry, can you?
It was important to the rank for identity, otherwise this does not work. So the way
Yeah. Yes.
you take all eigenvalues.
Yes.
So first you get in the span of UNP, and then in the orthogonal span.
No,
Then you can find out.
You're absolutely correct. You're absolutely correct. So it was important that this matrix was identity.
It's and for example the spectrum has earlier everywhere to spectrum of the eigenvalue. Now not all the eigenvalues.
हाँ, ठीक है. तो let's handle Piyush's concern. So Piyush is pointing out a very legitimate concern that this will not work if I can't extend this argument directly. So let's do the following. So let's do the following.
Proof after this is trivial to go from this to general case.
Yeah, I mean you're trying to look at the determinant of this
But
guy.
that does not go via this fact that rank 1 of weights can.
No, it does. So this is equal to determinant of A.
No, that I'm saying. This is just an algebraic argument after this. I'm
Yes.
not concerned about the proof of the general case.
Okay.
What I'm concerned about this statement is that all other items are equal one follows just for rank 1 of weights. It's not so obvious.
Oh.
I mean, like what is all? I mean, for example, what has happened is that otherwise there was a whole set of eigenvalues. Like you could take any vector to the eigenvalue. Now what has happened is that now they have been broken. Every vector that is orthogonal to V is to an eigenvector. But in the span of V and U, things have changed. U has become an eigenvector.
In the span of V and U, yeah, yes.
So there are no other
But the change is very predictable. That change is.
that is what requires. So the origin of the eigenvector.
So you're saying कि
You say it bit more.
okay,
Right?
okay.
So if you found one eigenvector, then any then we can try to find another vector like this.
No, but you work in the span of U perp, right? You work in the span of U perp.
So you first look at the span of UNP and then the perp of UV.
No. So what I'm claiming is that so let's see the details.
No, you cannot work the span of UPerp because it's not symmetrical. The eigenvectors are not necessarily.
No, I mean for the identity, in the identity case, so what I'm claiming is that if you look at I plus UV transpose,
Yes.
I'm claiming that one eigenvalue of I plus UV transpose is 1 plus V transpose U.
That's fine.
Right? I'm claiming, that you agree. I'm claiming that.
I don't agree with the proof that because of the rank of response, that proof requires a little bit more. Right?
Because what I will do next is that I will work in the span of U perp. So hear me out. Maybe you go ahead.
So once you have this, then the general theorem does not require anything. It's just algebraic.
The proof is merely algebra. Yeah. So okay. Just one moment, please. I'm sorry, right? So I want to say this for the rest of the class also. So what Piyush is claiming is that look, if you believe this, if you believe that all the other eigenvalues are 1, the remaining proof is just algebra. कुछ नहीं करना है, बस ये काम करना है कि बाकी जगह ये लिख दो, I plus A inverse U V transpose. ठीक है, उसके बाद बाकी क्लेम हो जाएगा, determinant of factor out हो जाएगा and determinant of this guy, ठीक है, तो हो जाएगा. The concern that Piyush has is that he is disputing the statement that this thing follows, this thing follows, this thing follows. So yeah, this thing follows because of rank 1 update. That's what Piyush is disputing. And I'm trying to.
Yeah, like, for example, I was not identity, there will be
Yes, go ahead.
So, of course, we can remove I just had one to the eigenvalue.
Yeah.
What we are saying is V transpose has only one non-zero eigenvalue, everything else is zero. As long as
UV transpose is exactly one eigenvalue. That's another thing, right? I had.
No,
There is
No, no, no.
orthogonality around one. There is no orthogonality eigenvalue.
Sure, sure, sure.
if I may make an argument. So, what would you say for all the vectors perpendicular to V?
Yes.
Which
Yes,
makes
yes.
for dimensional space.
Yes.
If you let's say that U is not perpendicular to V.
Yeah, that's right. But now do another argument about when you. That's all I am saying. That one has to go through these cases. And actually, one.
But the case is direct, right? I mean, what like Mehul pointed out is that if you look at UV transpose, it's a non-symmetric matrix.
Yes.
But this non-symmetric matrix, it's has like one eigenvalue, one eigenvector is like V itself, right? U. One eigenvector is U, right? U. UV transpose times U comes out parallel to U. Yeah. Then
one eigenvector is U.
yeah,
And then what? It may not even have a complete basis of eigenvectors.
it may not have a complete basis of eigenvectors. That's
Because
right.
in certain when we are back. So
But for a rank 1 matrix, you can say that all the other eigenvalues are 0, right? It can have only one non-zero eigenvalue. All the other eigenvalues, complex or not, they have to be 0. All the other eigenvalues, complex or not, they are 0.
yeah, that's fine. But
So that works.
some
Okay. So I'm going to like request Piyush, if like you want, you can come on the board and so go ahead.
I mean, it's a simple thing. The proof would just be this, right? So you just, like, I mean, there are many ways. One would be just to say that you can actually produce a whole set of eigenvectors, which is what I think.
Yeah, which is what Mehul is saying.
So basically, what you say is that you work in this space, which is at most, 2-dimensional, maybe even 1-dimensional, and then there's a whole orthogonal space.
Yeah.
The orthogonal space is not changed. There, all the eigenvalues are 1.
Yes.
In this, you have found U, and orthogonal to U. I mean, by looking at things that are like orthogonal to V in this space, you can find one more, which is also 1.
I mean, the other argument is just this, right? Ki UV transpose has one eigenvalue, which is like, V transpose U. UV transpose is an eigenvalue, V transpose U, this thing. And all the other eigenvalues are 0. UV transpose is rank 1. All the eigenvalues are 0.
And importantly, that it is, it has a basis of eigenvectors, which is what
It has a basis of eigenvectors. Yeah. Sure.
Yes. The argument would be if we take
Actually, yes, instead of eigenvectors, so we just say. So another thing is because ideally you can as well say that this, let's say one of these things is actually EI. Then you're just writing it on a matrix.
Okay. Yeah.
It's like 1, 1, 1, and some entries here.
Yeah.
And,
Okay.
Like 1 plus something here.
So like I also need to like break out for lunch. But thanks for like that correction, Piyush. I actually would love you guys to be harsher because like this is my first time teaching this, right? And
it's fine. It's just that because
not Sherman Mauritian. This is not my first time teaching Sherman Mauritian. This is my first time teaching graph falsification. So yeah.
because that one I have had trouble with that myself.
Okay.
Because these things can be subtle.
Yeah, but I mean, like what Mehul said is the correct argument, right? What Mehul said is an correct argument in addition to others. Yeah.
It's an argument that basically has to say that where the one's eigenvectors come from. That is important because so A was some other matrix.
Yeah.
Just the fact that rank 1 update will not.
But like in the interest of time, we will break, and Piyush will continue it outside. Okay, so like let's go for a break.